Hey kids, welcome back to Mr. Murray's Math Land here. Today we are tackling what's called the disk method for finding volumes, part of the volumes of revolution or solids of revolution as they're called in calculus. So here's an example. Number one, consider the region bound by f of x equals 4 square root of x, the x-axis, and x equals 10. Okay, x equals 10 is that vertical line right there, and the x-axis right there. So we're talking about this region. Kind of obvious, but whatever. Find the volume of the solid obtained by revolving that region around the x-axis. Ooh. So not unlike the cross-section problems we've been doing where that's the base and now there are cross-sections kind of standing on top of it, we're taking this region and revolving it around the x-axis and making a solid. So can you visualize that? If not, let's go to a little demo here. So we're back on this site called GeoGebra, which has some cool demos in it. I don't know how people set these things up, but they're very cool. And here's our graph. F of x equals 4 square root of x. You can see this here. The x-axis, 0 to 10, that's the region we're talking about. And we're going to revolve it around the x-axis. So again, we're going to go 3D. So let's see if I can get this to, there we go. Now I don't have the z-axis, drawn for you right there, but that would be standing up. But here we go. There's sort of the flat plane of the xy axis. And now we're going to revolve it. So notice I'm going to take this slider and I'm going to slide this and very cool. So you can see that rotating around. Also notice the value here that when I make a full rotation, notice that's at 6.28. That should be familiar. That's 2 pi, right? One full revolution. But okay. But now let's see the solid that's formed. I think you can kind of visualize it. But let's see the surface here. Let's see what kind of figure we're talking about finding the volume of. And so now as we revolve, you see you get this kind of bell-shaped object here, and you can kind of spin around and see it from some different angles, see it straight on. So that's pretty cool, right? Very cool. So it's a little bit different. We're finding volume, but it's not, we're doing it by revolving this around an axis, not by considering that region to be the base of something. And whenever we revolve it around an axis, that's going to make circular cross sections, which is actually going to make things easier. So you'll see in a moment, this is why we call this the disk method. Because any section you take of this is really just made up of a lot of little circles compressed. As you get closer to that, tip of the bell, the circular cross sections are very, very small. As you get close to the end here, the circular cross sections are very large until you get to the end, and that's the largest circle of them all. And so it's the same premise that if I can add up that area of the infinite amount of circles that we have there compressed together, that will yield the volume of this. So it's really the same idea as our cross section. We're going to find the area of each cross section and integrate that to add them up and accumulate them to get that volume. Okay, so the important thing though is how do we describe that radius? And this right here, the axis, that's the red dot there, that's the x-axis. That's what we're revolving around. That's our axis of revolution. And it's not always going to be the x-axis, that's what's important. But this radius of each circular cross-section is that distance between the curve and the axis of revolution, or in this case it would just be the y value on 4 root x. But it's always what you want to describe is the radius here, because if I know the radius of a circle, I know its area, and the radius is always that distance from the outer edge of the region to the axis of revolution, to the middle of that solid. Okay, so let's go back and grind out the algebra here. So okay, we're back. Let's find the volume of this sucker here. We have these boundaries for the region. We know that it's going from 0 to 10, so I don't need to find that intersection unless I wanted the y value, and that will be doing that down the road. But again, just to visualize here what's going on, you're revolving this around there, so you're getting big circles or infinitely thin disks, and for each one the radius is from that axis of revolution to the outer edge of this region, and that's your radius. Okay, so our radius is always what you want to take care to define with these problems, and the radius in this case is just like we said, the y value on this, and the y value is 4 root x. At any x value you're at, that height is going to be your radius. Well, what's the area of a circle? Pi r squared, or in this case pi times 4 root x squared. So the same idea with our cross sections, we're just going to get the volume by integrating that area. So I like to put the pi out in front. That's a constant multiple, it can be factored out, and this r is 4 root x squared. We're doing it with respect to x, with the x-axis here, so dx, and we're going from 0 to 10. So our limits are 0 to 10. If you'd like to simplify this, you could square this, and actually, not necessary, but it might be easier for you to work with, that would be 16 root x squared is x. But if you're afraid you'll make a silly mistake, then you don't have to square it. But there's our volume. You could factor the 16 out if you like. And again, that could be done by hand, but we're beyond that stuff by now, right? 0 to 10, 16x dx. There's that. Multiplied by pi, 800 pi. You could leave it in terms of pi that way. Or if you want to get the real approximate value, that'd be about 2,513.274. $2,513.274. All right, pretty cool, right? So just to summarize here, it's the same. It's not really its own formula. It's just the idea of a circular cross section. It's just that a circular cross section is always going to have the area pi r squared, and the r is the important thing to define. You're going from A to B. The pi is always going to be there. You're always squaring it. And r, that radius of rotation, is always the distance from the outer edge of the region to the axis of revolution. In this case, that was the x-axis, but oftentimes it's not going to be. And when you want to describe that distance, if you're going vertically, perpendicular to the x-axis, that distance, that radius, it's a common phrase that keeps coming up, can always be described as the top boundary minus the bottom boundary. In this case, it was 4 root x minus 0, so just 4 root x. Okay, let's just try one more here. All right. So number 2, find the volume of the solid obtained by revolving the region bound by f of x equals x squared minus 2x minus 1 and the line y equals 7 about the line y equals 7. Okay. So this is important, that this is what we're revolving around. That's our axis of revolution. It's still a horizontal line, and just like the x-axis is horizontal, so this means it's just another version of the x-axis, meaning you're going to be doing it with respect to x, dx. And tomorrow we're going to be doing things around vertical axes, and that's going to be dy. But just that to keep in mind. So here is our graph, region bound by these two graphs. We want to find where these intersect. It's not given, so of course x squared minus 2x minus 1 equals 7. That's what I'm trying to solve, to find these 2 points. Even if you do it on the calculator, you better show me that equation that you're solving. I'm going to solve this one by hand. I just won't respect myself if I don't. Well, I don't respect myself anyway, but I'll respect myself less even if I don't. So nice factoring there. We get x equals 4 and negative 2. There we go. So this one must be the 4. That's the negative 2. Seems about right. Okay, so there's our region from negative 2 to 4, and we're revolving it around this line. So that means we'll be going around this. So some people like to kind of draw just to visualize what we're doing here. And there's where your circular, that was pretty bad, but those are where your circular cross sections are going to come into play. This axis is the center of those circles, right? You're going to have in the middle here, you're going to have like a big circle. And what's the radius of each one of those discs, each one of those circles going to be? Ooh, well, I went the wrong direction because that graph isn't really there. It's this graph, so I'm going to draw my radius in this direction. And so that's your radius, that's your radius, that's your radius. But it's the distance between this graph and this graph. And so again, the top minus the bottom, you know, this bigger y value minus this smaller y value, this y value minus this y value. That's going to give you that positive distance. So your radius is going to be 7 minus x squared minus 2x minus 1. Top minus bottom. And nowhere in here do these boundaries change. It's always 7 is always the upper boundary, and the parabola is always the bottom boundary. So we don't have to worry about setting up two separate integrals and switching them or anything like that. So I mean, in terms of what you're about to do, you could leave this if you like. Sometimes it's nicer to type into your calculator if you simplify it a little bit, though. Just distribute the negative maybe. 7 minus negative 1 is going to give you 8. Minus x squared plus 2x, however you want to arrange these terms. But that's your radius. So your volume is going to be pi from negative 2 to 4, the integral from negative 2 to 4 of that r squared. Pi r squared, and integrating them all with respect to x. Gonna do that one by hand? You could. Why bother, right? Okay, so throw a pi out here to begin with. Math 9, negative 2 to 4. What happens if I get a negative volume? That means you did something wrong. So don't just make it positive. Go back and fix your integral. Negative x squared plus 2x. Close that, square it. Just don't forget to square your radius. And here we go. We get about 814.301 or 300 if you like to truncate. 814.301. All right. Pretty cool. Hopefully you enjoy the disk method here, and it makes a little sense seeing two different examples. If you have any questions, of course, just hit me up. Have a good day.